Always, I'm making sure to record us going through the notes and stuff for today to make sure that if anybody ever wants to go back and hear me go through the notes again and kind of follow along with the notes, then you'll be able to do so by going back and watching this video. It'll be posted right up at the top of our classwork page under the September 30th chemical reaction. Can you guys believe that? It is the last day of September today. Freaking blew my mind when I realized that earlier this morning. I was like, all right, so tomorrow is Thursday, not September tomorrow. Good Lord. So September 30th, chemical reactions, because that is what we're going to be going over today. How do these different chemicals and atoms and compounds react to one another and cause some of those chemical changes that we talked about earlier in the semester? So our notes are down here, chemical reactions and equations. So because we have a short week this week, since this is our only class period on Zoom of the week, we have just one set of notes this week on chemical reactions. And then next week, we'll actually get into the chemical equation in a little bit more detail. So that's kind of what's going on right here. So as always, notes posted right here, September 30th notes, chemical reactions. So today we're going to talk about ways that you can tell that a reaction is happening, some of the different types of reactions that are out there, and some of the main characteristics of reactions when it comes to atoms and the energy that's present. All right, give it a second to load everything up, and then we will jump into it. Oh, I see a couple people have already started looking at the notes. That is awesome. All right, so chemical reactions, ways that chemicals interact with one another in order to create something new. So you may have heard me talk about changing one thing into something new before, and that's when we were talking about chemical changes. So if you remember back a couple weeks ago, we talked about how physical changes are when we take one thing and make it look different, but it's still the same thing, like shredding up a piece of paper. Whereas on the other hand, chemical changes are when we take one set of chemicals and we end up with different chemicals, a different set of substances. The process by which that happens is called a chemical reaction. So there are a lot of different chemical reactions that are going on every day in the world around us without you maybe even thinking about it or realizing it. So we have these chemical changes happening where we start with one set of substances and we end up with a totally new set of substances. So some kind of common everyday ones include growing. So it could be this little caterpillar right here. It could be the dog or cat or you or your kids in your house, right? Kids are known for growing, especially fast, as I'm figuring out on a daily basis. And so whenever something biologically grows and gets bigger, that's because it's been eating food, whatever it uses for food, and chemically changing that food into new cells, new tissue, and new energy. So the food goes into your body breaks it down into its little pieces, and then the cells in your body rearrange those pieces into new proteins, new fat molecules, new bone molecules or muscle tissue. And over time, if you're at the age where you can still get bigger and taller, you have growth happening. So again, we're changing substances. We're taking some leaf cells and turning them into caterpillar cells and energy chemicals. Similar things happening over here with ripening going on. So this is a tomato that was plucked off the vine before it was fully ripe. And you can see, if you've ever seen pictures or video of tomatoes growing, or if you've ever grown your own tomatoes, you know that they start off as these little hard green balls, and then over time, as they ripen, they get bigger and juicier and turn more red colored. Same thing with bananas that you might buy at the store. When you buy them, they might be pretty green on the outside. And then after a couple days, that green turns to yellow and they go from being sort of starchy and chewy to being a little bit sweeter and squishier. Then if you leave them too long, they get brown and gross and kind of sticky, sweet, and mushy on the inside and not good. That's due to chemical reactions happening that ripen that fruit. So we're taking the chemicals that are there and changing them into different ones that maybe give the skin a different color or that give the inside a different flavor. On the flip side of that, you have decomposing. So after something's been sitting out way too long or gets buried in the back of your fridge or your pantry and you forget about it for a couple months and then the smell leads to it, it's decomposing because the bacteria and mold are growing on that substance and turning whatever that substance was originally into food and energy for the bacteria and mold. So it's a very similar process as growing, only these guys are eating and breaking down these big structures into food for themselves. And then finally, a chemical reaction that we talked about a little bit when we mentioned chemical changes is burning, setting stuff on fire, combustion. So like I mentioned, we're taking these logs and through a chemical reaction with the oxygen and the air around them, we're getting smoke going up into the sky and ash left over in the bottom of our fire pit. This change happens due to a chemical reactions. The smoke and the ash that are left over are different sets of chemicals from the wooden log that it started out as. So these are just sort of some general everyday chemical reactions that are happening in the world around you, all about changing one set of chemicals into a new set of substances. So say you see something changing and you're not quite sure if it's a chemical reaction or not, or what exactly is going on. Well, there are a couple different signs that could point you in the direction of figuring out if something is in fact happening due to a chemical reaction. One that we talked about back when we talked about the chemical changes is bubbles appearing. So I mentioned the example of like dropping the Alka-Seltzer tablet into water. That causes a chemical reaction between the tablet and the water, and all of that foam and bubbles start coming up and popping at the top of your glass. Same thing with if you ever mix vinegar and baking soda together, and it creates a big foamy mess that starts spewing everywhere. That's because of a chemical reaction between those two chemicals. Now, obviously, something like bubbles appearing in boiling water would not be a chemical reaction because that is just water going from liquid water to gas water. It's still water, it's still H2O. We haven't changed it. Bubbles are appearing because of all of the heat that we're putting into it, not because of a chemical reaction between the water and something else. Another less common thing that can form in a chemical reaction is a new solid that gets formed, which in fancy science terms, sometimes we like to call it a precipitate. And essentially, this is something that happens in certain chemical reactions where you mix two liquids together, and then all of a sudden you end up with like some solid material in the bottom of your beaker or your test tube. So just like with the bubbles appearing where there weren't any before, same thing with a solid appearing where there wasn't one before. If that happens, it's a good sign that some sort of chemical change is going on. If we get a color change of our substances, so like we were just talking about with the bananas and the tomatoes, we go from green to red in the case of tomatoes, or yellow and then brown in the case of bananas, that is also due to chemical reactions happening inside of those fruits that's causing them to ripen. So those sorts of color changes indicate chemical reactions. A color change that is not a chemical reaction would be something like if you took a whole big jug of water and you poured in some purple Kool-Aid and mixed it all up, and now your water is purple. That's not the type of color change that we're talking about. That's a very obvious color change that has a very obvious reason for why it changed. You added some purple into the water, and now it's purple. However, if you mixed two clear liquids together and that turned purple, that would be a sign that a chemical reaction happened. Again, there was no purple before, and then all of a sudden we made this mixture and now there's purple there. Temperature change is a good potential sign of a chemical reaction. We mentioned the fire from earlier. Fire is very hot when a combustion reaction is going on, so it's giving off lots of energy that's raising the temperature of that area. Same thing with little hand warmers. So these are not really things that we need in Texas all that often, but I lived in Ohio for 5 years, and over the winter, one of my favorite things to buy at Walmart were these little hand warmers. They come in these little square packages, and you tear one off and crinkle it up when you're ready to use it, and that'll start a chemical reaction inside of that little packet, and then you slip it under your glove or under your mittens, and it keeps your fingers nice and toasty warm when you have to go outside when it's like 11 degrees outside, which sucks, by the way. I would not recommend moving somewhere where it gets to be 11 degrees if you can avoid it. So those little hand warmers heat up because of a chemical reaction with the chemicals inside of the hand warmer. When you force them to interact with each other, they have a chemical reaction and produce heat. Light can also be a really good sign of chemical reactions. We've already mentioned with the combustion reactions, not only do we get heat from the fire, but we also get the flames giving off a whole bunch of light. Same thing with things like fireflies in nature. So fireflies have the little abdomens that light up at nighttime, right? They produce those really pretty kind of greenish yellow colors. That light is being given off due to a chemical reaction in the firefly's abdomen. Obviously, they're not burning anything in there because that would be bad, but there's a reaction between a protein and a certain substance that when they interact, they release light as part of that chemical reaction. And then finally, if there's a really significant change in smell or taste, that could also tell you that something's changed on the chemical level as well. So with the fruit example from earlier, again, going back to that one because it's just so good, that banana, if you peel it and eat it when it's green, it's really starchy and kind of chewy and not very great at all. When you eat it when it's yellow, it's yummy, delicious, the banana that we all know and love. If you wait until it's brown, it develops this really kind of sticky, sweet, gross flavor, and it's all mushy and it smells kind of funky. And that's due to that ripening reaction that's going on. And so as the starch molecules in the banana get broken down into sugar molecules for chemical reactions, that's why we have that change from starchy to sugary. But if we let that go on too long, all that starch gets converted into sugar. So there's not much left to provide structure or to provide a balance between the starch and the sugar. So here we have some different examples. So here are some bubbles forming in the bottom of this beaker due to a chemical reaction going on between whatever substances are in here. Another good light example is this jellyfish right here. So some jellyfish, similar to the fireflies that we talked about earlier, will give off light due to a certain reaction inside of their cells. And when this happens in nature, we give it a big fancy name called bioluminescence, which basically just means things that are living, that's the bio part, give off light from their cells, the luminescence part. And so just like with the fireflies, these guys have certain molecules that will interact with each other, and when they do, they produce light as part of their chemical reaction. All right, so again, all of these are things that happen over the course of a chemical reaction to let us know that something has changed in terms of the substances we're dealing with. We get bubbles where there didn't used to be bubbles before. We get some new solid forming when we just mix two liquids. There's a color change that happens that we weren't expecting. All of a sudden, our substance gets really hot or even really cold as well. That could be another sign of a chemical reaction. If light starts being produced while the reaction is going on, or if a change in smell or taste happens. All of these things indicate that we no longer have the same set of chemicals that we started with. We've developed a new set of chemicals, a new change. All right. Any questions so far about the different signs of chemical reactions? Anything that anybody wants me to go back and review again?
Fine.
All right, maybe not. Okay, if you do think of any questions or you're having trouble getting through on your internet, you can always stick them in the chat and I'll check on them and give y'all updates when we take another little pause. So those are some signs that you could have a chemical reaction going on. So again, just to review, these chemical reactions are when we have one substance, one or more substances, and we convert them into new substances. And because it's science, we have specific words to tell us the substances that we're starting with and the substances that we are ending with. And we like to show it happen sort of like a math equation, where instead of an equal sign, we have this arrow. So the things that we are starting off with, the substances that are reacting with one another, are called, unsurprisingly, reactants. So our reactants are our beginning substances. This is what we are starting off our chemical reaction with. They are the ones that are reacting together, hence their name. As you may notice, as we go through today, scientists, not the most creative when it comes to coming up with names. They like to be as straightforward and direct as possible. So when we're talking about what is produced at the end of our chemical reactions, what do we end up with? Those are called the products. So we start off with our reactions. They react with each other and go through some sort of chemical reactions, and that yields our products, that creates our products. So the products are our ending materials, what we end up with after our chemical reaction is all said and done. So we start with our reactants, they go through the chemical reaction, and we end up with a different set of chemicals as our products. Again, if we started and ended with the same chemicals, we would not have a chemical reaction on our hands. In order for the reaction to be happening, we have to start off and end with different sets of elements and compounds. So that's one of the rules when it comes to chemical reactions. Our starting stuff in the reactants and our ending stuff in the products has to be different. One of the other rules is that chemical reactions only rearrange the atoms present. So we don't add in anything that is brand new, and we don't destroy any of the atoms that are there. Instead, we just change up how they're bonded to each other. And so what I'm about to show you guys is the equation for photosynthesis, which is how plants turn sunlight, carbon dioxide, and water into sugar in their cells. And it's going to look like a big complicated reaction, but I'm going to make sure to point out the important things to take note of. So here is our photosynthesis equation. On our reactant side, in terms of the different chemicals, we have carbon dioxide, CO2, and water, H2O. If you remember, we talked about these guys the other week when we were talking about compounds. So we have two different compounds here, CO2 and H2O. And then in the presence of sunlight, these guys will rearrange their atoms in a chemical reaction and produce in the products oxygen, O2 over here, and glucose, which is a simple sugar molecule. One of the most basic ones that there is. So 6 carbons, 12 hydrogens, and 6 oxygens make up glucose. Again, we start off with one set of substances in carbon dioxide and water, and we end up with a different set of substances, glucose and oxygen. So the first major thing to notice here is that we have the same types of atoms, the same elements on either side of our reactants and products, right? So over on this side, you may notice, actually, hold on, let me. Whoops. Stupid. Zoom, there we go. That's a little bit better. So on this side, we have carbons, oxygens, right here and right here, and hydrogens, right? So C's, O's, and H's on our reactant side. On our product side, we have some C's, we have some O's, and we have some H's. So notice we have the same set of atoms on one side as the other side. They might be present in different amounts. There might be different numbers of them. And because it's a chemical reaction, we've changed how they're associated with each other, right? So we've added some H's to get glucose, and we've taken some H's away from the water to make just pure oxygen. But we have not created or destroyed any atoms, right? There's a C in the reactants, so there has to be some C's in the products. There are O's in the reactants, so there have to be O's in the products. There are H's in the reactants, so there has to be H's in the products. We can't get rid of any of these atoms. We can only rearrange who they are attached to. Also, you notice that we haven't added anybody over here. So there's no like nitrogen, there's no aluminum, there's no gold that somehow got added into our products over here, right? None of these guys. Only C's, O's, and H's because we started with C's, O's, and H's. So again, we're only rearranging how these atoms are bonded to each other. We're not adding in any new elements, and we're not taking away any of the elements that were there. If there's a type of element in the reactant side, there has to be at least one of that element in the product side. Again, maybe they're in different numbers and amounts, and we'll talk about this a lot more when we meet back on Monday and talk about chemical equations in more detail. But if we have C's, O's, and H's on one side, we have to have C's, O's, and H's on the other side. So that's what I mean when I say rearrange atoms. I mean that we have the same types on either side. We just change up how they're arranged, how they're bonded together. And that is what gives us our different substances. So the way that the atoms are arranged on the reactant side gives us some carbon dioxides and some waters reacting together. The way the atoms are arranged on our product side is different. So that gives us some glucose and some oxygen that are our remainder. So we're changing which substances we have, but only by rearranging the atoms that make up those substances. All right, I know this can be a little tricky when we first talk about it. So anybody have any questions about chemical reactions so far and what's happening with these atoms on the reactants and product side? Any questions about this chemical reaction stuff?
Is that so? Like, since you have like the plant right there, right? That's plant, right?
Yeah.
That's how the plant grows, by those different chemicals that you were talking about.
Yep, exactly. So the plant will take in carbon dioxide from the air and water from the ground. And in the presence of sunlight, it can do a chemical reaction that changes that carbon dioxide and water into oxygen, which is kind of like a byproduct. So it just gives that off back to the air. But the main thing it wants is the glucose, because the glucose, the sugar molecule, is what it's going to burn for energy later on down the line. So they're making essentially their own food. It uses glucose for food, essentially, and it makes that food by combining carbon dioxide and water together in a specific chemical reaction.
Okay, so we don't have to really water it that much, the plant that much when we're doing stuff.
It depends on what type of plant that you have. Some plants are really good at surviving on just a little bit of water every now and then, and some plants need a lot of water because plants can also lose water to the environment. They have a process called transpiration that's almost like sweating, like what we do. So not all of the water that you take in by drinking gets peed out later, right? Some of it is lost when you breathe out because your breath has some water vapor in it. And some of it is lost if you sweat and put out water on the outside of your body.
Okay.
You can also lose water by having it evaporate to the atmosphere. So the plants that are really good about keeping that process slow don't need a lot of water, but other plants like tropical plants are not good at regulating their water, and so they always need a lot of water.
All right, gotcha.
All righty. Yeah. I always forget that they leave the pictures on there. Slide. All right. So I mentioned how our atoms are conserved and rearranged, right? We're not adding new atoms or getting rid of atoms in our reactions. The same thing happens with energy. So energy is also cannot be created or destroyed as we go through chemical reactions. Sometimes chemical reactions produce a lot of energy, and sometimes they absorb a lot of energy, but there's always the same overall amount of energy present at the beginning of the reaction versus the end of the reaction. What changes is what that energy looks like. So we can transform that energy from one form into another. So like take for a super simple example, a light bulb. A light bulb takes electrical energy and transforms it into light energy, and by a byproduct also gives off a lot of heat energy. So 3 different types of energy going on. So the electricity goes into the light bulb. Through the filament, some of that energy from the electricity is used to produce light, and a lot of it is used to produce heat, depending on what type of light bulb that you're dealing with. This would be like more of like an old school, old time light bulb. The total amount of energy is the same at the beginning and the end. Just like how with our atoms, we had the same types of atoms at the beginning and end of their reaction, we just transformed them from one form into another. Same thing with energy in a reaction. Like in this case, we have 100 units, say quote unquote, of electrical energy going into our light bulb. And 5 of those units give off the light that allows us to see, and 95 of those units are lost to the environment as heat. They're given off as heat as the light bulb lights up. So we still have 100 units of energy at the beginning and 100 units of energy at the end. They just got transformed from one form into another. So this is really similar to what happens with our atoms. We don't create or destroy any new atoms or lose any atoms that we had. We just transform or rearrange the atoms that we start with to the atoms that we end with. So we start off with C's, O's, and H's. We end with C's, O's, and H's. We just change or transform or rearrange how those atoms are attached to each other. Same thing happens with the energy that's needed for different types of chemical reactions. So if you take the photosynthesis example that we just talked about, photosynthesis requires sunlight to work. So the plants get the energy needed for this chemical reaction from the sunlight that comes in from the sun through our atmosphere. So they transform it from light energy from the sun into chemical energy in the form of that glucose. So whether or not we store that glucose in things like fruit, or we just store it inside of our cells, that glucose is what's going to be used as energy for the plant later on. So there's a different set of chemical reactions that'll take that little glucose molecule and transform it into energy molecules. Or maybe the plant won't get that far because we could eat the plant. And in that case, we're taking that plant's chemical energy and transforming it into our own chemical energy. So we're eating those grapes or that plant. We're breaking down all the different structures and absorbing that glucose. And then our cells can use that glucose to create energy. So we started off as light energy from the sun, but we transformed it into chemical energy inside of the plant. Again, we're not getting rid of any energy. We're not adding any energy in from nowhere. It has to come from somewhere. In this case, it's coming from the sun. So that's why we mean by energy is not created or destroyed. It's just transformed. So when we're looking at chemical reactions, they can fall into sort of 2 major different types. Reactions that produce energy or reactions that absorb energy. So if something produces or releases energy into its environment, that's called an exothermic reaction. So exo is a fancy Latin prefix that means out, going out of something. And then thermic is like thermal for heat or energy. So exothermic reactions are energy going out, energy being released into the environment. In general, exothermic reactions tend to heat up their surroundings because of the energy that is being released by these reactions. So we're releasing energy and the surrounding area is absorbing that energy and getting a little bit warmer. So eating food is a very good example of exothermic reactions. Just like I was saying earlier, how the plants capture energy in glucose and are going to use that for food. When we eat the plants, we take that glucose and we break it down ourselves, and that is what releases energy that allows our body to move around, to stay warm on the inside. So for everybody, your internal temperature, if you're healthy, should be 98.6 degrees Fahrenheit, which is usually quite a bit warmer than the surrounding area. So you're constantly having to burn this chemical fuel to digest this food in order to keep up that internal body temperature. Decomposition, similarly, also an exothermic reaction. So that mold and bacteria that's getting onto your old crusty bread or that piece of fruit that fell to the back of the fridge and has been back there for a couple months, that is also breaking down chemical structures in order to release energy. Only in this case, instead of us eating stuff, it's mold and bacteria decomposing stuff. Also, obviously, burning fuel and things like combustion reactions is an extremely exothermic reaction. So when we burn fuel, it produces a lot of energy in our cars, and that energy is what gets used to turn the axles that'll move your wheels. The energy also produces a lot of heat. That's why the hood of your car feels really hot after a little while, because combustion, burning fuel, is a very exothermic reaction. It gives off a lot of energy and heat. Some exothermic reactions, like burning fuel, also may give off light. So obviously, digesting food inside your body isn't really producing any light. But burning fuel, setting things on fire, or that bioluminescence that we were talking about in the fireflies and the jellyfish earlier, all of those are exothermic reactions where instead of the energy being given off as heat, it's being given off as light. So obviously we have our little burning match over here, and we have a very exothermic reaction going on at the end, right? So the chemicals in the match head are combining with the oxygen in the air, and the friction from striking it against the side of the matchbox is what produces that chemical reaction where we have lots of heat and light in the form of fire coming off the end of our match, resulting in a very exothermic reaction. So exothermic, energy going out releases lots of energy. On the flip side of that, we can also have reactions that absorb and store a lot of energy. These guys are not exothermic reactions, they are endothermic reactions. So endo is another fun Latin prefix, meaning into or inside, going within. And then again, thermic, meaning thermal, like heat. So we have heat or energy going into the reaction. So we're absorbing energy from the environment. So usually endothermic reactions are what is used to produce large chemical structures. So chemicals that need a lot of chemical bonds in order to be formed usually require a lot of energy to get there. And so we have to absorb that energy from the environment. So maybe it could be heat energy that is giving us the reaction that we need. That's why a lot of cooking and baking requires you to heat stuff up on a pan or to put stuff in a hot oven, because cooking and baking, there's a lot of chemical reactions that go on, but usually they require some sort of heat to get started or to be fully completed, right? You can mix the flour and eggs and sugar and butter all you want in a mixer, but let it sit there on your countertop, nothing's gonna happen, right? It needs that heat in order to chemical reaction and become something delicious, like a cake or cookies or something like that. Sometimes with really powerful endothermic reactions, we can get enough energy being absorbed from the environment that it actually causes a temperature drop. There's not too many that do that, but it is possible. It can happen. So a really good example besides baking of an endothermic reaction is one we were talking about just a little bit earlier with our photosynthesis. So we take our carbon dioxide and water and use energy from the sun. So this is a type of chemical reaction that requires light energy. So the energy from the light and the sun is enough to change this carbon dioxide and water into that big sugar glucose molecule that we're going to use for energy later, and that oxygen that we give off. So that glucose, that big 6-carbon sugar molecule, that requires a lot of energy in order to be constructed. And so we absorb the energy in order to do that. If you're a plant, you absorb it from the sun. So exothermic reactions are all about producing energy, giving off lots of energy to the environment, usually creating a lot of heat and maybe sometimes some light that gets given off as well. Whereas endothermic reactions, we're absorbing energy from the environment. We're using energy around us in order to create large structures in the form of chemical bonds. So in order to put lots of covalent or lots of ionic bonds together, we need energy from the environment in order to do that. All right. Any questions about the different types of chemical reactions or about any of the chemical reaction stuff in general that we have gone over so far? Any questions from any of this stuff today?
Well, I am just curious. This is Jessica. What about solar panels? Is that endo or
So solar panels
or
are also endothermic reactions.
okay?
Similar to plants, they're also absorbing energy from the sun in the form of light energy. Only instead of storing that energy as chemical energy in the form of sugar, solar panels store it in the form of electrical energy. So we store it in batteries that we can then send out that electrical energy to our house or to the energy grid later on. So that is another excellent example of an endothermic reaction. We're absorbing energy from the sun and transforming it into electrical energy.
Okay, thank you.
Yeah, no problem. Great point, great observation. All right, since it sounds like nobody else has questions at the moment, I just want to show you a little bit about the assignments they have for today and tomorrow. Since you had to deal with the whole midterm stuff last week, I tried to keep these ones super basic for you guys. So today's assignment is pretty straightforward. You essentially just have to go back to the notes and list out those 6 signs that a chemical reaction is occurring. So if you remember, it was things like bubbles or color change or light being given off. So I just want to know, what are all of the 6 different ways that we can tell that a chemical reaction may be happening with the substances that we are observing. So that is part 1 that got posted for today. The part 2 of that, which will be posted tomorrow, that you can do to get your attendance credit, is another really simple one that should hopefully only take you a couple minutes. And this one, I'm essentially just asking you to kind of compare and contrast exothermic and endothermic reactions. So I just want you to tell me a little bit about what is an exothermic reaction, what happens in one, what tells us that something is exothermic, versus the characteristics of an endothermic reaction and what is going on there. Again, as always, to help you work through those, you can always go back and double check on the notes and the chemical reactions section of the Google Classroom. And I'll also be posting a video of the class from today and the chemical reactions Zoom videos up here at the top of the classroom. Alrighty.